Um, my name's Martha Lewis. I'm from the University of Bristol in the UK. And my talk's on compositionality in conceptual spaces. So just a little caveat at the very, very beginning of the talk. I'm only going to, I should have sort of put a particular kind of compositionality in conceptual spaces. So there's lots and lots of research in this area, and I'm just going to talk about one particular sort of strand of it. But I will go ahead. So I'm interested in, I've been working in kind of conceptual spaces since my PhD, which was about 10 or 5 to 10 years ago now. And so I've been very interested, of course, in Peter's work, and it's great to hear his talk as well. And what I'm interested in at the moment in concepts is really concepts and how they compose sort of linguistically. So I've got here 3 sentences, which you can just sort of read. And as you read them, you'll be forming sort of ideas and thoughts about what's being expressed by these sentences. And that's done. You're doing that sort of on the fly, in a way that you if you don't know particularly about black mambas, you might not, all this stuff is new. And we're also doing things quite interesting, sort of interesting forms of composition. For example, like the metaphorical composition here of lift themselves, or held onto its seat, for example. So when concepts compose, they do so in masses of very interesting ways, and we can form completely sort of new ideas that we'd never thought about before. So why am I interested in this kind of linguistic composition? Well, first of all, it's just interesting, like how we can manage to do that. From a sort of more kind of engineering point of view, I'm actually currently in the Department of Engineering Mathematics. So from that point of view, computational resources that we use are becoming more and more prevalent. So many of us use computers on a daily basis. We're talking on computer now. You may be using your phone to look things up. There's going to be the language being used in the home, and as we interact with computers, it would be nice to do so within this with a sort of natural language way of doing so. And furthermore, on the right hand side of the screen here, as these things do become more and more prevalent, we want to do it in an explainable fashion. So whilst deep neural networks are incredibly successful at doing these kind of linguistic things. Here's a budding linguist here who's learning lots. Mom, can you? I'm just giving a talk at the moment, my love. Thank you. Sorry about that. So whilst deep neural networks are of course super successful, it's not always very clear how they do what they do. So part of what we want to do is have something explainable there. And we want to do more than just model words. So we might have a good way of modeling individual words, but we also need to look at phrase and sentence meanings. So, for example, things like natural language inference or natural language understanding, question answering, and so on. We have to model sentences and not just the individual words in them. Okay, so that's a sort of general motivation for why I'm interested in compositionality. Here's an outline of the talk. I'm going to talk about something called categorical compositional semantics and how that can be applied to conceptual spaces. And then I'm going to dive in a little bit more and talk about hyponymy relations between words and entailment, also ambiguity and metaphor, but I'm going to do that in a slightly, not quite a conceptual spaces model. It's actually, so Thomas was saying before we went live on this webinar that one of the previous sessions was all about quantum theories of cognitive science, and these the work I outline a little bit later on in the talk has some links to that as well. So there's a nice connection there for if anyone here is interested in that sort of thing. So here's all that, like, well, not all, but here's a load of work that I'm not going to talk about, which is about compositionality in conceptual spaces. So there's, of course, Peter's own work. I've just put the dates of his books, but there's masses of work about how concepts, models for how concepts compose, how to represent different kind of parts of speech and compose them together to form descriptions of events, for example. There's work by Rickard, Esbit and Gibbon, who talk about a formulation of the theory of conceptual spaces and indeed how to compose concepts together. Similarly, Adams and Raubal, Bechberger and Kuhnberger have talked about composition, and there are many, many more. So if you're not on this slide and you think you should be, I apologize, but you just need to go to Google Scholar and look for compositionality in conceptual spaces. You'll find lots and lots of stuff. What I am going to talk about is this model of categorical compositional semantics. So there are dictionaries for words. Why aren't there dictionaries for sentences? And of course, this is because we can take words and we can put them together and form meanings of sentences without having to look that up in a dictionary. So how do we kind of do this? So on the one hand, we might represent meaning within a kind of conceptual space or vector space sort of format. So we have on the right hand here, we've got this image. This image is actually taken from one of Stephen Schockhart, Joaquin Dirac and Stephen Schockhart's paper on conceptual spaces. So here you can see that that concepts are represented as kind of regions of a space, and we have that some regions are contained within other regions and so on. There's also vector-based models of meaning where words are represented as vectors in a vector space. But on the other hand, there's on the left-hand side of the image here, we've got this sort of compositional model of meaning where we can compose words together, and we get a representation of a sentence, which we then plug in sort of truth values to do with the individual words in the sentence and come back with a truth value for the sentence overall. So this left-hand side, the sort of logical side, is very good at modeling composition, but maybe not so good at modeling how to represent the meanings of the individual words. But the more sort of the conceptual space, vector space models of meaning are very good at representing the individual meanings of the words. So how can we combine the two? And we're going to do it in the following way. So we're going to build up sentence meanings using the grammatical structure of a sentence. So on the one hand, we're going to have some sort of continuous model of the word meanings, so as vectors, regions, and so on. On the other hand, we're going to have the grammar of the sentence, and we want to combine the two together to form the meaning of the sentence here: smelly baby cuddles dad. And the method that we use, so originally this was originally proposed in 2010 by Cook, Sadrazadeh and Clark, with reference to a kind of vector and tensor-based model of word meaning. And the idea is that the grammatical structure maps into the bottom of this diagram. We have these cups underneath that tell us how words compose together, and the meanings of the words slot onto the top of the diagram. And I'm going to go through in a little bit more detail what this kind of means with reference to conceptual spaces in particular. So first of all, I'll talk about the grammar that we use. So on the previous slide, we had a sort of grammatical structure here that you're probably quite familiar with. Well, if you're familiar with sort of grammar in general, you might think of, so certainly in English, a sentence dividing out into a noun phrase and a verb phrase. We've got this noun phrase dividing out into an adjective and a noun, the verb phrase dividing out into a transitive verb and a noun. And as we go back up the tree, it tells us how to compose these to form the sentence. We're going to use something slightly different here called pre-group grammar, which has the same, it's the same in the sense that we are taking individual parts of the words and so individual types for words and composing them together. So a pre-group, so if you like this sort of thing, a pre-group is a partially ordered monoid with left and right adjoints. So what does this mean? It means we've got a set P of kind of individual types. Our types are just going to be N and S. We've got a multiplication here, which in this sense is just going to be putting types next to each other. The one is the unit. We've got an order on these things, and we've got these adjoints, which tell us how we can cancel certain elements out with each other. And it's called a pre-group because it's like so a group would have these left and right adjoints would just collapse into one single inverse, and then we'd have and this would be equality. But it's not, it hasn't quite got there, so it's a pre-group. So these inequalities here say, so if we've got an element X, and we put the left adjoint of X to the left of an X, then we can reduce that down to 1. And similarly, if we put the right adjoint of an X to the right of an X, then that also reduces down to 1. And there are also these type introduction inequalities, which I won't talk about right now. So in the grammar that we're going to use, we've got a couple of basic types. So we're going to use N for noun and S for sentence. And then, at least in English, the type of a transitive verb we model as right adjoint of N concatenated with S concatenated with left adjoint of N. And then if we, to kind of type out to give a sentence the type, we'll have N, so we've got clowns tell jokes. So that's a noun, a transitive verb, and a noun. So we have our N, our noun type, this composite type, NRSNL for the transitive verb, and then again an N for the noun type. And we'll see that this left adjoint of N to the left of this end cancels down to 1. This right adjoint of N to the right of this end cancels down to 1. And we end up with S. And so what this says is that this string of types here reduces down to S, which means it's well typed as a grammatical sentence. So if anyone feels like interacting, you can put something on the chat. So can anyone guess what has the type in English, NNL. It's different in lots of other languages, but in English, the type is NNL. So I'm going to quickly open the chat and see if anyone wants to guess. I'll give you a couple of minutes. No, a couple of seconds. Okay, no one wants to have a guess. That's fine. So in English, the type, something with type NNL is would be an adjective. So we had, so if I go back to this this diagram here, we see we've got this type here, smelly, has the type NNL, and then baby cancels out with the NL, and we get a noun type, smelly baby. Sorry, a noun phrase, smelly baby. So how are we going to map this over to conceptual spaces? So I apologize, I haven't sort of done a background of what conceptual spaces are. Peter mentioned, talked about them briefly in his talk. So we have the idea that a concept is going to be represented as a region of a space. And in this particular model, we're going to say that the region has to be convex. So we're going to map our noun type to a convex space N. So a convex space is just a space where if you take 2 points in the space, every point between it is also a member of the space. We're going to map our sentence type also to a convex space. This concatenation operation is going to be Cartesian product of these spaces. The adjoint ends up just being isomorphic to the original space, and these reduction operations end up being a relation that kind of picks out matching elements in the space. And this is described in this paper by Bolt et al. It's published and also freely available on the archive. So we find we have this model where the pre-group grammar and the representation of the concepts and words themselves have the same underlying mathematical structure. And specifically, we're going to model individual nouns as convex sets, so convex regions of a space. And we're going to model functional words like verbs and adjectives as relations on the space that send convex sets to convex sets. So these are convexity preserving relations. So if I have a convex set for baby and I apply smelly to it, I get back another convex set for smelly baby. So as I said, and as I think Igor alluded to, or Peter alluded to in the question time, convexity is quite a strong, condition actually, and perhaps this could be weakened somewhat, in particular to kind of star-shaped properties. And I'm going to talk about a sort of short example here. Again, you can read about this in more detail in that paper. So as I said, nouns are going to be subsets of the conceptual space, and our noun space is also going to be divided out into different domains. So we have the color domain, a taste domain, and this is just a sort of made up domain of texture. So it goes from 0, which is liquid, to 1, which is very hard. And we have that bananas are quite soft, so 0.2 to 0.5. And then, so bananas have this color range from yellow, green and black, this sort of taste range from sweet to bitter, but not really sour or salty. Similarly for apple and beer. And we can then talk about how to compose concepts together to form sentences. So within this, we need to actually think about what the sentence space is. And this is still a kind of a question that I haven't really looked into in a lot of detail. So I'm not, I'd really like to hear people's sort of ideas on this. So your sentence space, if you want, could be something as simple as a space of true and false. And you might just want to assign truth conditions to a truth value to your sentence. But we can go a little bit more complicated, and we can say we're going to have a sentence space of good, bad, surprising, and unsurprising. So we have at the top here, we have the point that is good but unsurprising. Over to the left here, we have a point that's good and surprising, bad and unsurprising, and bad and surprising. And we would then set up some sort of convex relation for the word taste that relates bananas. So we'd have bananas taste sweet. And what we would want to do is relate bananas and sweet such that they map to the sentence meaning essentially good. So this is the sentence meaning good and surprising, good and unsurprising if it's a yellow banana, good and surprising if it's a green banana. So this is this kind of convex subset of the sentence space here. On the other hand, beer tastes sweet is going to be something like, is going to be bad and surprising. And that's this convex subset of one single point in the sentence space. So this is sort of how far we got within this paper. And I think the problem I was having with sort of progressing this line of thought was then how do we start learning these from from either text, let's say text corpora or other ways of learning them. How are we going to start setting up these the subsets themselves are the noun sets are maybe okay, but then the convexity preserving relations, they start becoming a little bit more difficult. So if people have ideas on this, I'd really love to talk to you and to maybe kind of set up some work together on this. I'm going to talk about some related work within the same vein. Vincent Wang modeled concepts within the same sort of conceptual spaces type framework as concept functionals. So the idea of a functional here is to assign a truth value to each point in the space. And we can then, he then showed that you can have the same sort of treatment where you can do this kind of grammatical composition of concepts, but you can also model fuzziness. So in the previous work, it was just crisp concepts. And so in this one, you model fuzziness and also negation. Another piece of related work was done by Sean Tull, where he models concepts as log concave functions. So the property of log concavity is expressed here. So if we have a fuzzy concept C, which takes elements of a set and maps them into the interval 0 to 1, this is log concave if the membership of any convex combination of 2 points in the concept is greater than or equal to this function of the membership of the individual concepts, individual points in the concept. And this is this was inspired by the sort of convexity criterion that Peter mentioned, that if you've got 2 points within a concept, you want all the other points to be within the concept as well. Excuse me. But having this, having if you ask for that criterion, it makes it more difficult to set up this kind of compositional framework. And this criterion allows you to set up the compositional framework where you can have the concepts compose with each other. So Sean Tull has this paper is available on the archive here, and he's also talked about modeling various different aspects such as metaphor as well. Okay, so just an interim summary of this point. So so here we consider noun concepts and sentences to be represented as convex sets within some kind of conceptual space. And then things like adjectives and verbs are maps. So adjectives map from the noun space to the noun space, verbs map from the noun space to the sentence space. And then we can set up a kind of compositional framework that allows us to then generate sentence meanings. So one of the really nice things about conceptual spaces is this fact that you have hierarchical structure just kind of automatically embedded within the space. So we have the relation of hyponymy, so the is a relation is kind of automatically in there, in that a concept like motor car is a hyponym of motor vehicle, just in case motor car is kind of contained within motor vehicle. And so we wanted to kind of leverage that kind of that useful aspect of conceptual spaces, but we're going to do it within a slightly different framework, which it was easier to kind of generate the right representations for. But it has the same, you can see it has kind of exactly the same structure, really. And I'll talk a little bit more about how we build these things. So in this framework, we have that nouns are things called positive operators, which are a kind of matrix, and you can vaguely think about them as, well, you can think of them as kind of collections of vectors, and then the verbs and the adjectives are maps that again preserve the positivity. So this is where we start linking to the quantum work that I alluded to earlier. So a positive operator we always work in real spaces. So on a real Hilbert space is going to be a linear operator. So that's a matrix, such that for any vector in the space, the inner product of AV with V is going to be positive itself. And the matrix A has the property that it's self-adjoint, and it's going to have all positive eigenvalues. And given a word vector V, so let's suppose we have a load of vectors for words at our disposal, which when you're working with these things, you frequently do. There are lots and lots of kind of ways of building vectors for words. So given a word vector V, we can lift it to a matrix associated with that vector. So if you're familiar with this quantum notation, you'll understand this. If you're not familiar with it, you can think of what you can think of, because we're only working in real vector spaces. You can think of this thing, which is called a ket, as a column vector, and you can think of this one as a row vector. So we have column vector times row vector, which gives us a matrix. And then we're going to think of more general terms like pet as being a sum or a mixture together of more specific terms. So we're going to have pet is going to be a combination of dog, cat, tarantula, and so on, where all of these where you're going to kind of list out all the elements that you want to put into your pet concept. So this is going to give us a matrix, and these matrices have a natural ordering. So the natural ordering is kind of a simple one, really. We say that A is less than B if B minus A, and that's just matrix subtraction of matrices, if B minus A is itself also one of these positive operators. And we're going to interpret this ordering as a hyponymy relation. So what we want is something like, we want to be able to say, like if A is dog and B is pet, we want to say dogs are pets, for example. And we have a graded ordering. So again, thinking back to dogs, if we say dogs are pets, well, that's not always the case, because we have, for example, working dogs, sheep dogs and things, which are not pets. But in general, so perhaps this links a little bit to this sort of notion of generics. We kind of want to have this sort of graded notion of containment between these operators. So we're going to build positive operators. We have techniques for building these positive operators. We can use off-the-shelf vectors such as glove or word2vec. And then we get information about the hyponymy relations from somewhere else. So we can get them from WordNet, for example, or you can actually kind of get information from text corpora themselves by looking for particular linguistic patterns in text called Hurst patterns that kind of signal that, for example, a dog is a kind of pet or a kind of mammal. And so using this information, we combine the projectors together to form matrices for words, which have this sort of internal structure to them. So that gives us individual word representations, and we then have some techniques for building phrases and sentences from these words. So I won't go into these in detail. If you want to know more, information, there's this paper by Bob Cook and Konstantinos Mykonetsis on the archive. Another paper with a group of us on the archive that talk about how you can start to compose these words together. But we essentially have a range of different sort of multiplication operators that preserve positivity of these, that preserve the right structure of these words. And then using these, we then kind of test them on some different data sets. So at the moment, we've just looked at very simple sentence data sets, and future work is going to be kind of extending these to larger kind of natural language inference data sets and so on. So firstly, we can look at single word relationships, so that, is cat a hyponym of mammal? And then we look at simple sentence entailment relationships. So we have, for example, summer finish should entail season end. And then we should also have, but that should be true, but then season end should not entail summer finishes, because it might be that winter is finishing. So with this, we get some nice results on this. And we've also extended this to modeling negation. So if we normalize these word matrices in the right way, we can then model negation. So we do that by saying we're going to take the entire space as modeled by the identity matrix. We can think of the identity matrix as a sort of projector onto the entire space. And then if we subtract out the matrix for the word, then we get another positive operator that we can think of as being the negation of the word. And this gives us good result on simple, again, very simple sentence entailment. However, so I think Peter mentioned this in the discussion. This is not really how negation works in conversation, and there's also been some work in looking into how to use these kinds of methods actually to model conversational negation. So conversational negation, you'd say, is marked by which sentences are appropriate to say. So if you say, that's not a dog, it's a wolf, that's an appropriate use of negation. If you say, that's not a dog, it's a chimney, that's not going to be appropriate unless, apart from under some slightly strange conditions. Okay, so an interim summary of this point. We can use word representations that have this inbuilt notion of hierarchy, and we can introduce a sort of negation. And these fit within the compositional framework that we want to use. So questions here is that we have this graded notion of hierarchy, and it would be nice to look at the properties of those gradings. Similarly, some more investigation into the properties of the kind of composition operators that we're using, building into other logical operations, so quantifiers in particular, and also extending to larger scale data sets. Okay, so I'm going to quickly talk about another use of these kinds of representation. So in the previous work, we were using this representation of a positive operator. Another word for positive operator you can think of as a density matrix, where we were collecting together instances of a concept. Now, in this use, rather than collecting together instances of a concept, we collect together senses of a word. So here we're going to use a density matrix, which is essentially a positive operator that's had a certain normalization applied to it. We're going to use a density matrix to represent a probability distribution over the senses of a word. So the word bank could be represented as a mixture of the sense riverbank and the sense financial bank. And then what we want is for words to, when we compose them together, according to the composition operators I talked about before, we want the sentence to kind of disambiguate automatically in the process of composition. So often when you look at word sense disambiguation in natural language processing, there's often a sort of pre-processing of let's disambiguate the words and then do the composition. But here we want the words to disambiguate as we're doing the composition. So this is just a description of how we actually learnt these word matrices. So in this case, we use an extension of the word-to-vec model. So I won't describe that in detail. Essentially, word-to-vec is a neural network model where the word vectors end up being part of this hidden layer here. And what we do is we, instead of learning vectors here, we learn matrices. We learn multiple vectors, and we then mix together the vectors. And we run experiments on these word disambiguation data sets. So we have, for example, if we have triples of sentences. So here we've got, for example, people buy house should be similar to people purchase house, but it should be dissimilar to people bribe house. However, of course, if you have something like politician buy journalist, then that's going to be more similar to politician, bribe, journalist. So this is the kind of structure of the experiments, and we get really nice results on this. So we're comparing with state-of-the-art like sentence encoders. So these are these deep neural network models that make sentences for vectors, and we either, well, in many cases we beat them. In some cases we don't quite beat them, but we get pretty close. So this was a nice result here. So interim summary of this part, we've got is essentially the idea here is that there's potential to also use neural network methods to build these sorts of representations. And it would be nice to develop these methods further. So it'd be nice to build these, not just to develop these, not just to build these sort of density matrix models, but actually to sort of do region encodings proper rather than what we've done here. Okay, so just to wrap up, so for future work in this area, I'm interested in looking at these sort of downstream tasks that we have. So things like looking more at natural language inference, text summarization, and so on. But also in moving to conceptual spaces proper. So really like looking at conceptual spaces where we want to look at regions of a space rather than these kind of matrices which don't quite encode a region of a space. And also ideally to start having these sort of meaningful dimensions along the space rather than the sort of not meaningful dimensions that you have in text processing generally. Also, everything that I've talked about has been with a sort of very static notion of meaning. We kind of work out what the words are, and then we compose them together. But it would be great to sort of move towards a more dynamic notion of meaning. We have started looking at these things as well. Okay, so in summary, for this, we've said that conceptual spaces can be formalized in a compositional way where we model nouns and sentences as convex sets and then functional words as convexity preserving maps between them. And then we can use grammatical rules to compose words to form phrases and sentences. We've shown that a variant of these ideas can be used to model hyponymy, entailment, and also ambiguity. There's potential to integrate these ideas more closely with neural methods to sort of use all these electronic resources that are available to us at the moment, these data sets. And essentially, there are lots of avenues to explore here. So thank you all for listening, and do fire some questions at me, and do get in contact if you are interested in talking more about these things. Thank you.